Welcome to the deep dive. You're here because you want to get under the hood, really understand things like AI, but without wading through tons of dense
Yeah,
text.
cut straight to the chase.
Exactly. And today, we're diving into Geoffrey Hinton's ideas. We're tracing that line from Hopfield Nets all the way to Boltzmann machines.
And looking at how they basically kickstarted the whole deep learning thing. It's quite a story.
It really is. And obviously, Hinton's recent Nobel Prize just highlights how important this work was and still is. So this deep dive, it's your shortcut to getting these foundational AI ideas.
Our mission, if you will.
Yeah, our mission. Figure out the core concepts, the problems they hit, and why these networks are still relevant today.
Okay, let's do it. Hopfield Nets, where it all began, more or less.
Right, so what were these things, fundamentally?
Okay, so a Hopfield net. Think of really simple neurons, like light switches, on or off, binary, one or zoomer.
Simple enough, on or off.
Yeah, and the key thing is how they're connected. Every neuron is connected to every other neuron.
Wow, okay, a real free-for-all.
Kind of. And the connections have weights, strengths, but crucially, the connection from A to B. It's exactly the same strength as B back to A.
Symmetrical, like a two-way street with the same speed limit both ways.
Exactly. That symmetry is important. So the big idea Hopfield had was that these networks could store memories, almost like how a physical system finds its lowest energy state.
Energy. Okay, now you're bringing physics into it.
Well, yeah, Hinton talks about a configuration that's just a snapshot, right? Which neurons are on, which are off at one moment.
Got it. Like freezing time and looking at all the switches.
Precisely. And for any snapshot, any configuration, you calculate its goodness.
Goodness. How?
You just sum up the connection weights between all the pairs of neurons that happen to be on at that moment.
Okay, add up the strengths between the active ones.
Yep. And the energy of that configuration is just the negative of the goodness.
Ah, okay. So high goodness means low energy.
You got it. And the network naturally wants to settle into states with the lowest possible energy, like a ball rolling downhill.
Makes intuitive sense. How does it actually do that? How does it roll downhill?
It's actually super simple at the neuron level. Each neuron looks at the total input it's getting from all the other neurons that are currently on, weighted by the connection strengths.
Right.
If that total input is positive, the neuron turns on. If it's negative, it turns off. That's it.
Huh. Just reacting to its neighbors.
Purely local decisions. But when you let all the neurons do this repeatedly, the whole network kind of shuffles itself around until it reaches a stable state.
Stable mean.
Meaning a configuration where flipping any single neuron wouldn't decrease the energy any further. It's found a valley, an energy minimum.
And Hinton gives an example, right, where it finds a better minimum.
Yeah, it might start somewhere okay, but through these updates, it can potentially find a configuration with even higher goodness, a deeper energy valley.
Okay, this is clicking. And Hopfield thought these energy minima, these stable states, could be memories? How does that work?
Well, the cool idea was, what if you could set up the connection weights just right so that the patterns representing your memories are these low energy states?
Ah, so you teach the network by making memories the preferred configurations.
Exactly. Then, if you give the network just a piece of a memory, like activate only some of the neurons involved,
It uses those local rule.
to roll downhill towards the nearest complete memory pattern. It fills in the blanks, cleans up the noise.
Content addressable memory. You access the whole memory just by knowing some part of it. That's clever.
It was a really elegant concept. But then Hinton, along with Terry Sosnowski, thought, okay, memory is cool, but what about perception, interpretation?
Taking it a step further.
They proposed adding another type of neuron. So you have your visible neurons, they get the actual sensory input, like pixels from an image.
The input layer, basically.
Right. But then they added hidden neurons. These aren't directly connected to the input. Their job is to build an interpretation of what the visible neurons are seeing.
So the hidden guys are trying to figure out the meaning behind the pixels.
Precisely. And now, the energy of the network's configuration represents how bad the current interpretation is. High energy means a poor interpretation.
So the goal is still low energy, but now low energy means a good, plausible interpretation of the input.
Exactly. Find the best explanation for what you're seeing. Hinton loves that ambiguous Necker cube example.
Oh yeah, the line drawing that can flip between two 3D cubes.
That one. The 2D lines are the same. That's the visible input. But your brain finds two different stable 3D interpretations. Those would be like two different low energy states in the hidden neurons.
Could they build a network that actually did that? Capture that ambiguity?
That was the goal.
Yeah.
But it's tricky, right? A single 2D line in an image could come from lots of different 3D edges in the real world. Different orientations, different depths.
Yeah, how do you represent that?
They imagine connecting a 2D line neuron to a whole bunch of 3D edge neurons, saying, any of you could be the cause. Excitatory connections.
Okay, lots of possibility.
But usually, you only perceive one edge at a time if objects are solid. So they added inhibitory connections between those competing 3D edge neurons.
So they fight it out. Winner takes all for that spot.
Sort of, yeah. It encourages one interpretation to dominate locally. And then they went further by adding connections between 3D edge neurons that would naturally join up in 3D space, like forming corners.
Making shapes emerge.
Right. And they even suggested making the connections stronger for edges meeting at right angles because our world has a lot of rectangles.
Building in a bias for common structures. Clever.
The hope was, with the right weights, the network would settle on patterns of active 3D neurons that formed a coherent, plausible 3D object from the 2D input.
Okay, that sounds really ambitious. But Hinton says it hit two big snags.
Yep. Problem one, the search problem. How does the network actually find that best, lowest energy interpretation?
And problem two, the learning problem. How does it get those right weights in the first place?
Let's tackle search first. Remember those energy valleys?
Yeah, the network rolls downhill.
Right. But what if it rolls into a shallow valley, a local minimum? It's stable there, but it's not the best interpretation, not the deepest valley, the global minimum.
And because it only goes downhill, it gets stuck.
Exactly. It finds a good enough answer and stops, unable to explore if there's something better over the next hill. Like taking the first okay parking spot you see, even if there's a perfect one closer.
So how do you get it unstuck? Give it a nudge.
Kind of. The big idea was to make the neurons noisy or stochastic.
Noisy.
Instead of strictly following the rule turn on if input is positive, off if negative, they make a probabilistic choice.
How does that work?
Well, if the input is strongly positive, it's very likely to turn on. Strongly negative, very likely to turn off. But if the input is weak, close to zero.
It gets fuzzy.
Yeah, it becomes more random. It might even make a move that temporarily increases the energy, goes slightly uphill.
Ah, that's the key. It can occasionally jump out of those local valleys.
Precisely. That little bit of randomness allows it to explore the energy landscape more thoroughly, increasing the chance of finding that deeper global minimum.
So noise isn't just interference, it's actually useful here. Now, what's this thermal equilibrium thing Hinton talks about?
Okay, so with these noisy neurons constantly flipping based on probabilities, the network doesn't just settle into one single state and stay there.
Right, because of the randomness.
Instead, it reaches what's called thermal equilibrium. This isn't a fixed state, but a stable probability distribution over all possible states.
A distribution, like some states are more likely than others.
Exactly. It's the Boltzmann distribution. States with lower energy are much, much more probable than states with high energy.
So even though it's fluctuating, it spends most of its time, probabilistically speaking, in or near those good low-energy configurations.
You've got it. So they're like a cloud. The cloud is always shifting, but it's densest over the low-energy areas.
Okay. And then Hinton realized you can use this for more than just interpretation.
Yeah, this is where it gets really cool. If you've trained the network properly and you let it run until it reaches this thermal equilibrium.
Without any specific input.
Right, just let it run freely. The pattern of activity on the visible neurons at that point can be seen as a generated image, an image the network dreamed up.
Whoa, so it can generate stuff that looks like what it was trained on.
Yes, because the equilibrium state favors low-energy configurations, and if the network learned properly, those low-energy states correspond to the kinds of patterns it saw in the training data.
So if you train it on cats, it starts dreaming of cats or things that look vaguely cat-like.
Pretty much. It's sampling from its learned probability distribution of what constitutes a cat image.
That's amazing. So interpretation and generation from the same kind of network. What then is the main goal of learning for these Boltzmann machines?
The ultimate aim is to adjust those connection weights so that the network's dreams, the images it generates when running freely, look statistically identical to the perceptions, the real-world images you feed it.
Make the internal model match the external reality.
Exactly. If you can achieve that, it means the hidden neurons must have captured the true underlying structure, the causes, of the data. Their patterns of activity would represent meaningful features of the input.
It's like the network learns what causes cats to look like cats, so it can then generate new cat pictures.
That's the intuition. It's constantly comparing its internal model with reality and adjusting itself. A very powerful idea about learning.
Okay, so how do they make it learn? Hinton mentions a surprisingly simple algorithm from '83. What was it?
It really is elegant. Hinton and Sednowski's algorithm has two phases, wake and sleep.
Wake and sleep, like us.
Kinda. In the wake phase, you show the network a real image, clamp it onto the visible units.
Force the input layer to match the image.
Right. Then you let the hidden units only settle into thermal equilibrium, influenced by that clamped input. While they're doing that, you look at pairs of connected neurons that are active together,
Okay.
and you slightly increase the connection weight between them.
Ugh, the Hebbian thing. Fire together, wire together.
Exactly. That's the wake phase, strengthening connections based on reality. Then comes the sleep phase.
Let me guess. No input.
Correct. You let the entire network, visible and hidden, run freely until it reaches thermal equilibrium. It's dreaming, generating its own patterns.
Okay.
And now, if a pair of connected neurons happen to be active together during this free-running sleep phase, you slightly decrease their connection weight.
Decrease. You weaken the connection. That seems weird.
It does. But the combination is brilliant. You strengthen connections based on real data, and you weaken connections based on the network's own internally generated fantasies.
So over time,
Over time, this pushes the network's dreams to become more like the reality it saw during the wake phase. It effectively lowers the energy for configurations corresponding to real data.
and raises the energy for configurations that are just the network's own made-up stuff that doesn't match.
You nailed it. It learns to prefer reality.
And Hinton emphasizes something amazing here, that this simple wake-sleep process gives each connection weight all the info it needs about all the other weights.
Yeah, that's the kicker. Just by comparing how often pairs fire together during wake versus sleep, each weight gets the right signal to adjust itself globally. It's statistically beautiful.
Unlike backpropagation, which needs that whole separate backward pass calculation.
Exactly. Hinton saw this Boltzmann machine learning as potentially more biologically plausible. It felt more like how distributed learning might happen in the brain.
A very appealing idea, theoretically.
Yeah.
But the big but, it was slow. Painfully slow.
Yeah, that was the killer. Getting these networks, especially large ones, to actually reach thermal equilibrium took a huge amount of computation. Many, many updates.
So elegant idea, but impractical for big problems back then.
Pretty much. It was a major bottleneck.
Okay, so the theory was cool, but stuck. Then, fast forward, 17 years? Hinton and colleagues figure something out. Restricted Boltzmann Machines. RBMs.
Yes.
The breakthrough.
What was the key restriction? What did they change? It sounds simple, but it was crucial. They removed all connections between the hidden neurons.
Wait, the hidden neurons couldn't talk to each other anymore, only to the visible layer.
Exactly. Visible talks to hidden, hidden talks to visible. But no hidden-to-hidden chatter.
How did that help?
Dramatically sped up the wake phase. When you clamp an input on the visible units, because the hidden units don't influence each other, they can all figure out their activation probability in one go. Parallel update.
Whoa! Instead of iterating back and forth, just bang, one step.
One parallel step for the hidden layer to reach equilibrium, given the input. Huge speed up.
Okay, that solves the wake phase bottleneck. What about sleep? Still needed equilibrium, right?
Technically, yes, for the pure theory. But they developed a brilliant shortcut called contrastive divergence, CD.
Contrastive divergence. Sounds fancy.
It's basically a practical approximation. You don't wait for full equilibrium in the sleep phase. You just do one cycle. Data in hidden activation, reconstruct the visible data fantasy. Get hidden activation again.
So data, think, reconstruct, think again.
Sort of. And you adjust the weights based on the difference between the neuron co-activations during the data step and the reconstruction step.
So you compare reality with a one-step fantasy.
Yeah, and it turns out to be a surprisingly good approximation of the full wake-sleep learning gradient, but way, way faster.
Fast enough for real applications.
Definitely.
Hmm.
Hinton mentions Netflix using RBMs, combined with other methods, for their recommendation engine. They even won that big prize, partly because of it.
Wow. Okay, so RBMs hit the real world.
Yeah.
But Hinton also said one hidden layer. Maybe not enough for really complex stuff like images or speech.
Right. A single layer learns basic features, but for hierarchical understanding, edges make shapes, shapes make objects, you probably need more depth.
So how do you get depth with RBMs? Just stack them?
That was the next big idea.
Yeah.
Stacked RBMs. You train the first RBM on the raw data.
Okay.
Then you take the activations of its hidden layer,
The patterns it learned.
and you use that as the input data to train a second RBM on top.
Ah. Learning features of the features.
Exactly. And you can repeat this. Stack layer upon layer. Each RBM learns correlations in the activity of the layer below it, building up complexity.
Learning correlations of correlations. That sounds powerful.
It allowed them to learn these deep hierarchical representations. And then came the final piece of that puzzle.
What was that?
Using these stacked, pre-trained RBMs to initialize the weights of a standard deep feed-forward neural network.
So you build the stack, let it learn unsupervised, and then use those learned weights as the starting point for a regular network you train with backpropagation.
Precisely. You'd usually add a final layer for the specific task, like classification, and then fine-tune the whole thing with labeled data using backprop.
Why was that pre-training step so important? Why not just start the deep network randomly?
Two big reasons. First, it made the final backprop training much, much faster. The network already had a good initial guess about useful features from the RBM pre-training.
Like giving it a head start. Hinton's analogy of a kid learning cow concept before the label.
Exactly that. Learning the structure first. Second, it helped the networks generalize way better, especially if you didn't have tons of labeled data. The unsupervised pre-training captured the essence of the data, preventing overfitting to just the labeled examples.
And this actually worked in practice. Big time.
Oh yeah. Hinton mentions the Google Android speech recognition system in 2012. Using deep networks pre-trained with RBMs gave a massive improvement in accuracy.
That feels like a real turning point, the moment deep learning started to deliver on its promise in the real world.
It absolutely was. It showed everyone that deep networks could be trained effectively.
But, as Hinton says, we don't really use stacked RBMs for initialization much anymore, right? He calls them an enzyme.
Yeah, it's a great analogy. Like an enzyme helps a chemical reaction happen but isn't part of the final product. RBMs helped catalyze the deep learning revolution.
They showed it was possible, broke the logjam.
Exactly. They proved deep learning worked, overcoming years of skepticism. Once other initialization methods and techniques were developed, the RBM pre-training wasn't strictly necessary anymore. But its impact was proving the potential of depth.
So their legacy isn't just the technique, but the shift in belief they caused.
Absolutely. And it's interesting, Hinton still seems really keen on the underlying Boltzmann machine ideas, especially that wake sleep or maybe just unlearning during sleep as a potentially more brain-like way to learn than backprop.
Yeah, he hasn't given up on that core concept.
Not at all. He thinks studying how the brain might use sleep could still lead to new AI breakthroughs.
Okay, what a journey. We went from Hopfield's simple memory networks,
To Boltzmann machines trying to interpret and even generate data using energy and noise.
then the practical speed up with RBMs, stacking them for depth.
And finally seeing how they acted as that crucial enzyme to kick off the deep learning era we're in now.
And it all came from relatively simple rules, like neurons influencing each other and trying to find low-energy states.
The complexity emerging from simplicity is really striking.
It really is. Which leads to that final thought. If Boltzmann machines learn by contrasting wake perception with sleep generation, maybe even involving unlearning, could our own brains be doing something similar during sleep?
Refining our internal models, tuning our own neural connections based on the day's experiences versus some kind of internal replay or generation.
It's a fascinating possibility, isn't it? What if sleep isn't just rest, but active essential learning and unlearning? Something to definitely chew on.
Absolutely. Hopefully this deep dive gave everyone a solid grasp of these foundational ideas that are still shaping AI today. Lots more to explore there.
Thanks for taking this deep dive with us. Until our next exploration.